Hi guys, welcome back to another LS-DYNA tutorial, and in today's tutorial we're gonna do modal analysis, meaning we going to find the natural frequency. It will have two parts, two files. We're gonna make two files. The first one is for a simple rectangular plate, and the second file, it will be a solid part and it is a bit more complex. So let's start off. So we're gonna make the shell plate first. So here you go to mesh, shape measure, and here you go for node shell 0 0 0. Okay, just copy and paste first like this, and then this one just copy this value, which is 2.35702. This is the second point, and the third point, this is y and x will be 25, and the last one here is 25, and you create. Okay, this part, let's say it's simple, it's represent a simple bridge. So what I can do, can type bridge here, then I can play with the number of elements. Here I put 100, let's say. Here around x will be 100. Can increase the mesh 20 and 200, and here you have it. Okay. Why we have this very weird number, later on later on you'll find out. Okay, now this is a shell, so it doesn't have a thickness, so we need to define the thickness. Go to model, keyword, and then click all, go down to the section, and then shell, new ID, bridge section, and then now the thickness will be 0.8485281, and the rest you don't need to change, accept. Now after we do that, we go and define the material. Just take the basic elastic material model, should be fine. This density is 2400. Here in this tutorial I'm dealing with kilogram in meter. I'm not using millimeters as usual. So this one will be kilogram meter cube, and this one E will be 27.5 gigapascal, Poisson's ratio 0.3. and these two actually are the material properties of concrete. Of course, for modeling the concrete in different simulations, you better use different material models, but for the time being, because we are just using modal analysis, this one should be fine. Okay, accept. Now we link the part to the section and material. This is the section, and this is, and accept. And here I want to check, measure what is the mass of this guy. Okay, 120 tons, or 120,000 kilograms. So that's the mass that I want. Alright, now we want to fix it at the sides. So boundary, one side will be simply supported, the other side will be hinged. Let's say this part will be hinged. Hinge meaning it only can rotate. So create, and then select, no, here I did not click this one, boundary SPC, create, and here by edge, then propagate. Okay, now we selected all the nodes here, so we say this one will be hinge, so it cannot move, doesn't have any degree of freedom except the rotation around the y-axis, so RY will be not fixed. Okay, now we go to the other side. This is the other side. This one will be simply supported, so it can move in X around, it can move along the x-axis. The other things are similar. Okay, so I can do also edge, propagate. Another way is click node, then area, then make the box, apply. So now you have two boundary conditions. Okay, so we define the parts, we define the section properties, we define the material, boundary conditions. Now we go to the keywords that we need to define for the modal analysis. It's under control, and then we have implicit dynamics. This one, make it 1 dynamic analysis. Then general, this one also make it 1 implicit. And then solution, implicit solution, control implicit solution, everything leave it as default. The same goes with implicit solver. Now the most important thing is implicit eigenvalue. Okay, so this is the only thing that you need to define. The other things are optional. Here, how many modes of vibrations or how many modes of natural frequencies you want to see. Okay, let's say I want to solve for 5, then accept, done. So I think that's everything. Now click on save, browse. Okay, I already have it here, I did it before, so I click on this, I overwrite file. Okay, now I open the solver. Okay, this is the file. See the time we just made it, the file that we just made it. Then this one, no need, the file is small actually. And done. Okay, now we need to open the result. Okay, so this is the result for the eigenvalues D3i EIGV. So you double click and you can open like this. Okay, this is because I'm using 4.5. If you are using the very old LS prepos, you need to open the D3 plot files first, then you drag the D3 eigenvalue files. Okay, so here you can see this is the vibration of our so-called bridge. This is the first mode, the second, and the third. Okay, maybe you see this one is very funny one, but to make it look more appealing, you reduce the scale factor and then reduce this division numbers, so you can see now it is more acceptable. Okay, here you see the first frequency is 2.08181. okay, and why actually we chose the values of this section in the material, because actually this is taken from this paper by Young et al 2004. okay, I will give the link of this paper down in the description, and I did a work based on this paper. So if you go down here to section 5 or 6, you see that here is the dimensions. See, the length is 25, this is E, and you see the fundamental vibration frequency of the bridge is 2.08, and what we got here is 2.0818181. so we can say that our results are okay. So that's all for the first file. Now we're gonna do the second one. So the next part, we're gonna find the natural frequency of a solid part, and that solid part is a stiffened panel. okay, and if you don't know a stiffened panel, what is a stiffened panel? It looks something like this, or closer view like this. Of course, we are not going to model the whole thing. okay, we're just going to do one part, this portion. okay, and by the way, this paper also, I will link it in the description, is by my supervisor and my colleague. okay, so here, this is the results file. We can close it. Here also we can just close it because we are done with this. Now we copy this one and then we name it Stiffened Panel. Copy, paste, copy the file, paste. Now we going to make the stiffened panel mesh, and we're going to use solid elements. okay, so this one can just hide it. Now since we say we're gonna make it as solid elements, okay, so here in the y direction is 14, and in the x direction, sorry, in the z direction is 11, and then the a direction we make it straight away 4150. okay, this one, these are in millimeters, so we change it to meters. okay, create. You might wonder what is this long thing. Doesn't look like a stiffened panel, right? So no need to worry, just follow first. In x, you can increase the number here along the x, y and z should be 1. okay, this is what we're making just a box here. In x, let's say I make it 100. yeah, should be fine. okay, now we can extrude to the top 200. this one mesh, element generation, and then solid, face drag, and the thickness is 200 millimeter, which means 0.2. segment we just put, let's say 3. this is in z direction, positive, and then click by element, propagate, and here you have. If you can see what I'm doing right now, I'm doing actually the web. so we can increase actually the number of segments. Make it like this. Okay, now we make another one, and this one is, the thickness is 11 millimeters and the segment is 1. Create. Now we make the flange, not this one. We F2, we hide this guy, and then we click by element and propagate. Here I have 100 minus 14 will be 84. 84 divided by 2 will be 42. So it will be 42, and then the direction will be in negative y, sorry. I can increase the number of the elements here. Okay, 3. Now I move to the other side, click here. Alright, now similarly I will make the other side of the stiffened panel. This is only one stiffener, then we're gonna duplicate easily. So click here. Now this one we need some math. 830 minus 14 will be 806, divided by 2 will be 403. 403. Then create. Okay, we can increase the number of the elements here, make it 10, or even make it, no, this is, yeah, make it 20. Accept, and then go here, make it negative. And then you can see we have it already. Okay, I'm not sure about this length, it looks very long. Eight, 4, 8, 2. Yeah. Okay, I missed the calculation. It's supposed to be 830, but this millimeters, but here is 820 millimeters. I think I missed the dimensions here. Okay, the dimensions are, can pick any of these, but seems correct. B, yeah, I think it is correct. So now I'm gonna duplicate and translate this part. First, I measure the distance that I want to move is this one. Then I translate in Y. This is the distance. I select by part 1, 2, 3, 4, 5, and copy elements. Okay, now we're done with this. Accept. Now we click here. Gonna make another 2 of these guys. Then click by elements, area, highlight this. Another one. Accept. Okay. And should have one more. Yeah. Should have one more. 1, 2, 3, 4. Okay, click by part. Okay, now you don't want, of course, to copy all of them. You need only one side. So I select by node, then by area. Now using the right mouse click. Okay, I make an area with the right mouse button like this. Okay, now I make another copy. Oh, I forgot to include this. Reject. Okay, accept. Now this area, copy. Okay, now seems okay. Alright, now there are different parts, so you can you have two ways to do it. The first way, you duplicate the nodes. I mean, you have to duplicate the nodes anyway, so that they will be attached together. And then you can use this one, move copy. So now all of them will be one part. Okay, you can select any part here, or you can make also new part. Let's say part number 10, call it Stiffened Panel. Now click everything, then apply. Okay, now you have your stiffened panel. Okay, so this is the guy. Now you see all the parts still here, so you need to delete them, otherwise they will give you error. Delete the bridge also, you can delete, and now you have this stiffened panel. Okay, section, this one of course is solid, so solid section, solid, then accept. Shell, this one you delete it, you don't need it anymore. And the material, let's say we take this one, it's made of steel, and this density is 7850. Okay, this one is 205.8 gigapascal, 0.3, and this one 315 megapascal, and that's all what you need. Okay, now you link all those together. See part here, section is a solid, material also solid, accept. Okay, now I want to make it one for fun, because I don't like this color, and this also I want to make them one. So I go to this one, concrete, I don't need it anymore, delete. This material number 2, change it number 1, and the solid section from 2 I change it number 1. Of course this is not necessary, but because I want it to be 1 1 1, just like that. Okay, boundary condition, this one I need to delete, of course, because this one attached to the old one, attached to our bridge that we destroyed already. So we see here the boundary conditions, we are making one of these. Okay, so the red one, no, we are actually make one of this, the blue, so we want the blue part. Okay, so this one cannot move in X. Okay, so all these cannot move in X. Yes, see it. Okay, sorry, cannot move in Z. This blue one cannot move in Z, and this one, it says rotation equal to 0. meaning it cannot rotate. So just to align it, same way, it's supposed to be something like this. Is it clear? I hope it's clear for you guys. Okay, so this side and this side, which is this and this, are not movable in Z. So boundary species set, and then create, it says displacement in Z equal to 0, meaning cannot move in Z, but in X and Y can move. Okay, so click by element, propagate. It's only the lower part. Okay, no problem. Is it hanging? Seriously? I think so, it's hanging. Oh, okay, good. Then we rotate the other side. We also can click here, then the front view, we unselect the webs and the flange. By node, again the same trick, make an area, pick, make an area with the right click. Okay, so this one cannot move in Z but can rotate. Okay, then accept. Now the other condition is this one, the black one, it's cannot move, cannot rotate in Y and in Z. So similar, but we just add this one, rotation in Y and rotation in Z. Now we do the same thing, click by edge, propagate, or click by element, propagate, done here. And this one, okay, sorry, okay, then accept. Okay, actually just now for the first part of the boundary condition, we can just select by edge, but that didn't come into my mind. Select by edge, propagate, like this, and done, and it's much easier. Okay, so now we save this one, control save, and then we just run. It might take a longer time than the first file because it is a bit bigger. Okay, done. Now we open this one. We have this file. This is the file of interest. Open. Okay, we did not fix in the Y direction. See how much the boundary conditions are important. So we need to do that actually. So we need to fix in the X direction. Yeah. So here can we just modify from here? Yeah, need to fix in Z and in Y. So the first part, this part cannot move axially like this, so it's fixed in X. And number 2 is these sides cannot move in Y. Okay, now we save. Done, saved. We close this first, then we rerun. And it's done. Now we go this file again. Now you can see the first natural frequency is 26.96, and if you play it, it will be something like this. Okay, as before, this doesn't look nice, looks like they are dancing and having fun. Make it 0.1. This is a bit slow, right? So make it 3 and make it 2. I can see now it's like they are really vibrating. Here you can, yeah, let's say resultant displacement. Okay, now we see the next one. The next one is like this, and it's 30.29. The next one is like this. This is the fourth one, and this is the fifth, which is the last, because we request only for 5 modes, that's why you have only 5. Okay, you can see 26, and this 30, this 32, this 34, and this 36. Okay, I think in this paper did not discuss anything about the natural frequency. Okay, so we cannot actually validate our results like what we did before. Okay, so I think that's all for today. Thank you, and see you next time. And don't forget to like and subscribe.